Hello everyone. Well, welcome back to Alkaline Hydroxide 784. Well, this is probably one of my favorite episodes in GP overview and we haven't even begun. Why you ask? Well, if you didn't already know, I like mathematics I mean, and that's why it gets my favorite number 28. By the way, did you know 28 is a perfect number? And the day that this video is being released, the 6th, is also a perfect number. Before you go around accusing me of quoting the devil, seriously 6? Well, a perfect number just means a number whose factors, apart from itself, add up to itself. So the first three perfect numbers, according to mathematicians, are 6, 28, and 496. To be honest, I actually remember the third one as well. And then I searched up to just, double confirm. So now you might be asking, was that trivia really necessary? This is a GP series, not a math series. So I searched what perfect numbers are used for. And this answer kind of sums up something that we'll be, realizing throughout this episode. So this is from one of those forums, and this person called Joseph Malkovich said that at the end, he told that one of his professors made of observation that if some mathematicians can create a nifty bit of theoretical mathematics, eventually someone else will find a nifty use for those ideas. So I think that's a pretty interesting point, and with that, I will make it like the starting of my GP essay here. So sometimes you don't know that something will actually be useful, but hey, for a lot of maths, something seemingly absurd and abstract ends up being very useful in some way. So yeah, before we go on this journey together, here are the timings, and of course they are embedded in the video as well. Let's start. So yeah, like an actual GP essay, let's for once in a long time look at what a lot of people think. That first paragraph that you write, only to dismiss it in the next paragraph. So when you tell someone that you like maths, you're confronted with, oh, you're very smart, yeah, or they can relate, maybe. Okay, so if you ask people who aren't in Singapore, maybe they might say that maths isn't that helpful for most people, especially, apparently in US, some people think stuff like calculus and things like that aren't so useful. And for us, maybe our context, the stuff that we learn in H2 maybe would be calculus and vectors, maybe stuff that not everyone finds useful. So what kind of math do people even do every day? Even for, adding up stuff, subtracting numbers, people just reach for their calculators. And yeah, I suppose even as someone who actually likes maths, I do wonder, is there a need to teach vectors to everyone? Oh wait, I just got word from my script that vectors doesn't exist in H1 math, so technically you have a choice not to take it. So let me see what H1 maths has, because that's like the bare minimum that you need to take if you go to JC, that is. So they have stuff like calculus, graphs, stats, PNC/probability. Okay, to be honest, most of it is actually useful for everyone. Yep, that will be our first 4 point in a sense. But before we go there, back to this, well, there are some topics that people will forget immediately, and even sometimes statistics, even though it's quite useful, people tend to forget, just forget them if they're not taking a maths relate, like a major that uses stats in the sense. Yeah, so that's pretty unfortunate. And the reason why I say unfortunate is because I have a counter to the fact that people think that maths is not very useful. Because there is, in fact, many math stuff that everyone needs, and we will get to that right now. So the first point is stuff that everyone needs for sure. So what I would say is basic arithmetic, and to a lesser extent basic algebra. It's always a handy way to quickly do some mental math, because you don't always have access to your phone calculator, and phone calculators are a thing of the 2010s and not before that. So it's useful to know your mental math, and usually you use it for maybe prices of objects. You go shopping, you want to add up the price of two things, and then prepare your money even before the cashier tells you to pay it. Maybe the number of things that you have, you want to add them up. Maybe you're planning for something and you need to add up numbers to figure out what you have to deal with, etc., etc. So basic arithmetic definitely useful. And algebra, well, I know the word problems in your exam may make no sense, but in reality, there is some logic to having such word problems. And the knowledge of algebra may be partially helpful in actual situations, even if you don't use the algebraic expressions or like say, oh, 4x plus 5 is some number or something. You don't say it that way, but you kind of do follow the same process in your head when you're calculating something and you work back to find the answer. So algebra does help. And apart from those, well, it also helps to know how statistics works. And for some cases, even some of the calculations involved in statistics. Even though you don't have to do the calculations yourself, you need to know what they mean, like how they work, or like what kind of calculations are done to get to the answer. But why? Why do you need to know this? Why does anyone need to know about linear regression and p-tests and whatever other tests they can create? Well, have you considered where statistics is actually used? Well, it's definitely used in a lot of research, a lot of it, including natural sciences, social sciences, engineering, health, and so on and so forth. And it's also used by many companies in advertising or by other groups who want to send a message. So you know what I mean, right? Like you see your advertisement with some statistic, like some percentage or some graph or something, then they try to tell you to buy their product. Or maybe if you're looking at activism, sometimes they say, oh, this many people are being affected by this problem and we want to help them and stuff like that. So that's what I mean. So who is the audience of all of this research and message sending? Well, it's all of you, I guess. And that means, you need to ask the so what. That means that you don't have to actually do all of the data compiling and the actual creation of the graphs unless you're the person who is trying to do the advertisement or the research. But you definitely do want to have more confidence in what you're looking at. You need to know that what you're looking at actually makes sense and it isn't some sort of manipulated fake data. And for that, stats is useful. And I've lost track of my script. Where is it? So, understanding precisely how statistics works is the best way to actually know that you're looking at the right data, or what is the correct stuff and what is the wrong stuff in whatever you're looking at. So if you know something, for example, terms like statistically significant, which you need to know what they mean. If, for example, you're reading a research paper or you're reading a news that says, oh, this research found something that was statistically significant or something like that. So you would need to know what that means, and you can spot any manipulated data if you know what I mean. So for example, if let's say the graph doesn't start from 0, which is the case in many places, sometimes they start from a higher number and for example, they put it at 20 to 30, then they show the temperatures of different places. Then the 20 to 30 difference will actually look really big because they started from 20 instead of starting from 0. So you can see the difference actually in a slide that I put here. It's just a random data set of temperatures from different parts of the world, I guess, And or another example is extrapolation or seemingly groundbreaking results. So extrapolation means that if you have a bunch of data points and you just draw a trend line, but you don't stop it at the data point, but you just drag it further on. Well, do you really believe the dragging on part of it? Because the results may be different in the future. It may not actually be a straight line upwards. It could go down again. It could just stay at one point. It could just do whatever you want. So extrapolation is not that reliable. Or even stuff like groundbreaking results, which could be the result of a very small sample size. Because if, let's say, if you use 5 people who appear to have this positive result, but then 95 of the other people have a negative result and you haven't tested them, then you conclude that for everyone is positive, the sample size is too small. So you got to do your research on the research in a sense. So that's why it's actually quite helpful to look up other sources of the same news to know whether the news is actually true. Anyway, that's a bit of a digression, but you get the point. If you want examples, you can watch the video links for one with relating to the claim that the U.S. election was rigged. The funny thing is that one was using this very weird statistical test, and they even used it in the legal suit, like that file that they give for the legal suit, and that's just crazy because it's not even correct. It was done in a very they used the wrong kind of test on the data. So yeah, you might want to watch the video for that. So if you prefer talking about research data specifically, well, I read a book called Dark Data. And whether intentionally or not, sometimes certain research practices can lead to data manipulation. So there's one very interesting example, like one very interesting practice called p-hacking, which involves including so many variables that there's at least one that meets the statistically significant criteria, which is usually 5%, in your p-test. So the other practices may be more suitable for an episode on research because they usually involve actually falsifying the data, which is not really maths anymore, just false information. But yeah, this is the most maths related one, which is because the logic is if you look at one specific set of variables, there are not too many. If they're not statistically significant, then that's about it. But if you look at enough variables, there might be one for which it may seem as statistically significant, but when you look at it from a larger point of view, the relation doesn't make sense. So you have to be careful about it. Stats is a very confusing thing sometimes, and you have to be very crafty and be careful about stats sometimes. So yeah, you just gotta know about stats in a sense. But of course, before we move on, let me just mention one last thing, which is stuff like calculators and Excel. So some people might say that since we have access to these, we may not really need our math knowledge to know how to do it. Okay, sure, but will you always have access to these things? Especially the calculator part. It's not that you're gonna be carrying. Sometimes your phone might run out of battery, and you may not have access to it. And another point is it also helps to understand how they work, especially for statistics. When you just put your data in Excel, which thing do you click? Do you click scatter graph? Do you click the bar graph? Do you click the histogram? What do you click? So you need to know what you're trying to do in order to click the right thing. And after you do that, you have your points there. Maybe you want to put a trend line. Do you put a linear trend line? Do you put a logarithmic trend line? Do you put a quadratic trend line? Or what kind of trend line do you put? Or and your axes, do you want your axes to be linear or in logarithmic form? Because there's actually a difference between the two of them, and in some cases it is more appropriate to use a logarithmic axis, whereas in most cases it is more appropriate to use a linear axis because there's also one form of data manipulation where they change the kind of axis in order to show it something significant when in reality there's nothing significant about the data. Yeah, so we are quite lucky that we do have this sense of innate ability to tell when the trend is not so linear or it is linear for sure. We can tell with our visual abilities. But at the same time, it's helpful to know some stats so that you can, be extra sure of what you're doing and not be confused about how to use your Excel sheet. Yeah, so all right, let's move one step up and see maths that is widely used in more, sciencey or more engineering kind of disciplines. And let's talk about vectors and calculus and stuff like that first, because I think those things are more understandable to your. And then after that, I'll talk about some other slightly weirder math videos, I guess. So yeah, for now, let's talk about the stuff that you all know. And we'll start with calculus, which is very easy to tell that it's useful because, if you take physics, you already know that it's useful because the velocity is the differentiation of displacement and the integration of acceleration. Yeah, this sounds like the most lame poem ever, but who cares? But that's not all. It's not just about physics. You can use it for many things in engineering. And usually when we try to find either the optimum or the equilibrium of something. So by optimum, what it means is like we try to make dy or df or dx equals to 0. And that could be either the maximum or the minimum. And we also use the second differentiation so that we can confirm whether it's maximum or minimum. And for example, I'll just give you like a random thing that I came up with. So if your variables are the amount of material and volume, because in reality you don't just use x, you will be having more than one variable. So I'll just do that. So the two variables are amount of material and volume of material that you use, and the thing that's dependent on it is the function of strength. And then you can optimize it to get the maximum strength for what amount of material and what volume of the container that you want to use. So how it works is we have a problem. Maybe let's say this is for equilibrium. For equilibrium, how it works is usually in chemical engineering. I know I'm a bioengineer, but never mind, let's just go with this. Let's say we have a factory process and there's some chemical reaction happening here. Yeah, so I'm aware this chem eng stuff and I also kind of suck at it, so I'll just try to simplify this for you. And we just write an equation using these processes, and we want to make sure that the system is in equilibrium, because that's what happens normally when it comes to things like these. You may start with an uneven rate, but eventually the amount of stuff going in is going to be equal to the amount of stuff going out. And from there, we can do some calculus stuff, use your calculus stuff to get stuff done, and bazinga boo, we get our answer. Yeah, so that's calculus. You can use it for things like this. That's basically the point. As for vectors, well, let me first introduce you to matrices because they're a bit more all-encompassing. And vectors are basically represented in matrices in a way. They're like column or row matrices for that matter. And we probably know what matrices are, right? Right? Okay. So funny thing is you can actually use matrices to solve simultaneous equations. So let's say you have 3 simultaneous equations and you type it in your calculator. Your calculator is probably just solving a matrix. Yeah. So that's one use already, and you can think of it in a real world situation, like maybe the customer gives you a bunch of conditions for which you need to, consider all of them in order to have a few variables in your product. And you can take those conditions and transform them into equations and then solve those equations in a matrix to get the variables you want. Or if you want a weird example, we have this thing called finite element modeling, which is actually more of a mechanical engineering thing or materials engineering kind of thing. And the way the software, you use a software, of course, please don't try to do it by hand. It will just drive you nuts. But okay, if you usually use a software to do this, and because you use more complicated stuff you use complicated things in the software, so it solves a problem that we want to, like, if you want to get some data or maybe the forces acting on the object, that's the problem. The way that it solves it is usually using simultaneous equations, and these equations come from mechanics, which once again I apparently suck at. Oh well, but yeah, it's like those how do I say, the stress and the strain equations. Yeah. So it uses simultaneous equations to solve it, and that's just math. It's just using matrices to solve things. So yeah, engineers can use these things. What about some more weird maths then? Like stuff that you probably may not have ever heard of. Unless you take like H3 or you are more of a maths enthusiast than I think you are. Well, may I present to you, as far as what I actually happen to know about or hear about, string theory, knot theory. Yes, there are two separate fields. Or maybe stuff like, if you know stuff like maths theory, which is more pure maths and used in cryptography, I think people have heard of that at least. So number theory involves stuff like numbers. So in cryptography, you use large prime numbers, and therefore number theory is useful for that. And graph theory, which is also a bit more well known, I hope, has already shown its usefulness in finding the shortest route, the path, as well as apparently in bioinformatics. I saw a lot of graph theory there, and I don't know why. But take my word for it, I'm not bothered to really explain how it's being used. But let's say you want to convert, or if you have two DNA strands or more than two DNA strands, and you want to find the most optimal strand of DNA that matches all of the other ones the best, one way to do it is to use graph theory and weighted paths. Yeah, there's weighted paths because different transformations have different levels of badness, or like not very optimalness in the sense. Yeah, so it was very stressful to come up with quote for this, so I'm not gonna talk about it. So what's up with all these weirder fields? Well, I could go and explain them in greater detail in a different video, but I'll just very quickly say some stuff about string and knot theory. Okay, so string theory is actually not just pure maths, it's something in physics, and it does involve some maths to it, so I am not very well versed in it. I have only heard of the name string theory. Just read the Wikipedia page yourself. Yeah, so string theory generally says that particles, like, assumes the particles to be strings, like small stringy things. I don't know how that works. I'm not exactly good at physics. Okay, so knot theory, yes, I do know a bit more about it. I even read like this small little book about it, which is quite interesting. And quite funnily, it has a trefoil. I don't know how to say that, but it looks like you can see what it looks like on screen. And this thing is equivalent to a 1 in number theory. So for non-math enthusiasts, I apologize in advance. And this is because the trefoil is immutable in knot theory equations. Yes, knot theory has equations. Wonderful. But anyways, it's used in actual knotting stuff, like to tie actual knots and untie the knots, as well as to show you how your earphone get all tangled. Okay, maybe not that. It's usually used to see how DNA can unknot itself in bio, or as well as like you want it to do it in the least number of moves possible. And by move, I mean cut the DNA and then rejoin it. Because if you reduce the number of moves, then the DNA has lesser chances of, becoming mutated or something like that. And these theories have stuff in common with each other. Yes, so they're all kind of related to each other. And with topology as well. Topology is about some geometrical stuff. And yeah, before you start asking me why I'm not a math major or something, let's move on. To bring some much needed entertainment to this episode, well, what better to do than to indulge in some recreational mathematics? Okay, not everyone's on board, but that's the thing. Recreational mathematics has this vibe that is, just fun and games and something only relevant to people who do math and nothing else. But hey, even recreational mathematics actually gets used in real life. But I think like one of the things that people might associate with recreational mathematics is game theory. If you don't even know what I'm talking about, then oops. But yeah, but I'm just kind of actually just kidding because game theory wasn't created for recreational purposes. It wasn't actually created for games. It was originally created for economical situations because apparently economics is like doing games. Yeah. But it was later used in recreational applications such as actual games like board games and card games and I don't know, base games as well, poker, backgammon, that kind of stuff. Yeah. But let's go into actual recreational maths examples. So most of recreational maths tends to involve either weird geometry or some kind of number pattern or sequence or something like that. And there's also other such oddities. And I think one example is just the perfect numbers that I mentioned at the beginning. And we don't know what they're going to be used for. Maybe cryptography because they're related to factors, I guess. So factorization usually is used for cryptography. But I'll tell you some other examples which definitely have some use or some relationship to actual real life things. So first off, if we look at number patterns, let's talk about maybe Fibonacci because everyone knows about that. Fibonacci is found in nature and sunflowers and everything. Great, wonderful. But I'm not going to talk about that right now. I just mentioned it because everyone already knows about it, right? So I'll be talking about I'll instead be talking about the Pascal's triangle. And I'm pretty sure there's actually a few people who know what I mean when I say Pascal's triangle, or at least the thing that they see on screen, it'll be something that they're familiar with. You would have seen it in primary school or somewhere. And there's more than you think there is. It's not just about adding up the horizontal rows to give you the powers of 2, or the fact that the rows actually spell out the powers of 11. It's not just that. There's also patterns within the diagonals. Yes, so you can get the square numbers, the triangle numbers, the hexagonal numbers, whatever numbers that you can get from that triangle if you go down diagonally. That's pretty cool. So what about in the geometry part of it? Well, in terms of geometry, I think the more common one that people know about is fractals. And fractals are these things that have some weird property when you keep subtracting spaces, but it's still not zero space. Or like you keep adding some smaller triangles, and then it just looks so interesting. Well, but in reality, you could use fractals to explain things like our coastline, the biology of things, and even nature in general, because they're not very defined by simple geometry. And the fact that fractals have a non-whole dimensionality, yes, in fact, fractals are supposedly having a dimension in between 1 and 2. Yeah, this is perfect for this kind of application. Another kind of geometry thing is, I suppose, the 4D version of a Mobius strip. If the Mobius strip itself wasn't enough, I can bring you the Klein bottle. Of course, we are not actually looking at a 4D object because the Klein bottle that you can create in glass is a 3D visualization of the 4D object. Yeah. But the thing is, it brings awareness to 4D things in general. And you might be wondering, why do you need to know what a 4D object looks like? What's the point? Well, it gives us insight on how to visualize more than 3 dimensions of variables. So for example, as I mentioned earlier, you don't just have a y against a x. That's too simple. In real life, there's more than one variable that you're dependent on. In fact, there's 3 or 4, even 9 different variables that you could have one thing being dependent on. And sometimes you really do want to see it in a graph form, but you do realize you can't really see above 3D. So for example, you can see y against x, or you can see z against y and x, and that's about it. If you want to do w against x, y, and z, you can't see all 3 of those variables in the same graph. It's not going to work for your eyes. And that's because we're also 3D beings, so we can't really see anything above 3D. And yeah. And in fact, we're not even seeing 3D itself. We're seeing a 2D image of the 3D objects usually, but 3D is the max that we can go. So these, looking at things like 4D versions of Mobius strips or other 4D objects can give us an idea of what's the best way we can try to visualize things that are above 3D in order to, make some better idea of how to deal with the data and not just have to rely on the algorithms directly. So apart from that, we have another thing called Penrose tiling. I think you've heard about it as well. Penrose tiling is this kind of tiling that can go on forever. Yes, it's infinite tiling. And it's not symmetrical shapes in the sense they're like 2 different tiles that somehow go on forever and they don't repeat the pattern. It's uncanny to say the least. And you might be wondering, how is this useful then? It probably just gives you some interesting wall design maybe. But in reality, you can use it to describe something called quasi-crystals. Because people have originally thought that crystals are all nice and orderly and everything. But in reality, crystals aren't as nice and orderly as you think they are. So there are many crystals that are actually more of quasi-crystal than actual crystal. And this helps you to understand that better. the fact that it can actually work as a thing. Yeah, so I could go on all day, but I'll stop. But if you are interested in learning about any of this in greater detail, or if I ever get the time to cover any of these in greater detail myself, I'm more than happy to make a whole video on these things. Of course, not as a GPO episode, but as a separate video, I guess. Anyways, as you can see, all sorts of math is useful, like maths in all kinds of fields and topics and everything is all very useful for us. And well, one last point before we end this. I did mention earlier the kinds of maths that everyone needs to know versus the more specialized maths, right? So now I'm going to make a quick case for why you should try to learn more than what's purely necessary. And basically, just a few points. It's very quick. So first point, maths is based on logic and is also pretty abstract. Thus, it helps us to understand abstract concepts better and be more logical. So what I mean is, usually there's some things that are just really abstract, and by learning maths, you can understand those things better, and also you get to learn some logic. Maths is based a lot on logic. So, it's helpful to know more than just basic maths because by learning other fields of maths, you can understand things from in terms of other perspectives, other points of view, the abstract world, that you can understand it better. And speaking of abstract world, the second point is maths is based on what we see in nature. In fact, there are some people who have this debate on whether maths is invented by humans or whether it was discovered by humans because it's literally just an abstracted version of nature. And hence it helps us understand the world better, quite ironically. For as complicated and confusing the world is, like, how complicated it may be, maths helps us to understand something that is so complicated and so realistic using something that's just so abstract and so removed from the actual world, which is quite ironic in a sense. And yeah, of course, who knows, there may be a situation where maths can help you. Okay, I'll stop. But yeah, speaking of that, I think I've completely driven you all crazy talking about my favorite subject. Even though I'm not a math major. And I hope you all have the same amount of appreciation for this subject as I do now. And remember that last statement that I said? Because maths may throw us multiple curveballs of weirdness, but honestly, there's gotta be someone who can bring their bat to hit a home run with these balls and find a new and important use for some otherwise obscure piece of math. Wow. If I actually wrote this in my GP essay, I would be so proud of myself. Unfortunately, I probably was not so great at doing this at the time. Okay, anyways, but if you do write it, please quote me. Okay, never mind. You don't have to. Yeah, as you can see, the main point is from the beginning to end, maths is useful in many places, and even if you think it's not useful, someone will try to find a use for it. That's the point. That's all. Yeah. I hope you find this video useful because this is my favorite topic, and the fact that it's not even 40 minutes yet just means that I've been talking so quickly that I managed to finish it quickly, and I've actually put a lot of thought into it in order to make sure that the episode flows very nicely. And that's why I still consider this my favorite episode because I put a lot of effort into it. Anyways, if you found this video useful, please press the like button and subscribe. And with that, I would like to say thank you and bye.